Let's see if you can solve this riddle. Imagine you're a scientist trying to figure out which of these atomic models makes the most sense. Which of these is the most accurate representation of an atom? You think long and hard on what kind of devices and materials you could use to finally settle this debate. Can you think of an experiment that you could conduct in order to find the answer? What would you need to conduct this experiment effectively? Pause this video now to try and figure out on your own, or continue watching to see how it's done. While you're thinking about the solution, you suddenly remember a special kind of particle called the alpha particle. Although we will go into more detail of what an alpha particle is and how it's produced in a later lesson, for now all we need to know is that it's a very fast moving, positively charged particle that is small in size, even by atomic standards. You wonder if you can use this particle to somehow figure out the charge distribution of an atom, and therefore figure out which of the three atomic models is the most accurate. You also determine that the material to test this against would be aluminum, because it's a fairly stable material. Since you're testing for atomic structure, any material should give you the same results, because all atoms have the same general structure. A metal like aluminum would just be the easiest to work with, because it's stable and can be found in the form of very thin sheets. Now on the periodic table, the aluminum element is denoted in this format, where 13 is the element's proton number, aluminum's, and it corresponds to the number of protons in the nucleus of aluminum's atom, also as well as the number of electrons orbiting its nucleus. 27 here is a nucleon number that shows us the total number of neutrons and protons in the nucleus. In other words, you could find the number of neutrons in the nucleus by finding the difference between the proton number and the nucleon number. But this is a standard notation for elements, and all of them on the periodic table follow the same format. So the plan is simple. You place samples of the aluminum metal sheets inside a vacuum tube, bombard it with alpha particles, and use an alpha particle detector to capture how the particles are being scattered at different angles. Now, using a vacuum tube to house the aluminum metal is important, because you don't want the alpha particles to interact with anything other than the metal sheet, and air molecules can get in the way of that. So we make sure we remove all the air by using a vacuum. Now, before you can start the experiment, there is just one small problem to solve. You want to make sure that the source of alpha particles is releasing them at a constant rate. This is because if the particles are decaying and bombarding the sample at various rates, the detector too will capture those varying amounts of these particles, which will affect the results of the experiment. We also need to ensure that the particles emanate at roughly the same speed, because the speed will affect how much the particles are deflected and alter their paths, because that's what we're checking for: deflection and the angles in which the paths change. Once again, inconsistency in speed will affect the result of the experiment by changing the number of particles detected at different angles. So you can use a source that produces a constant rate of consistently fast moving alpha particles. Now that everything is set, you can conduct the experiment with aluminum samples. But what are you exactly looking for? Well, you know that aluminum metal sheets consist of aluminum atoms packed together. If these atoms are in the form of the third model, that is, they have a dense nucleus at the center that consists of protons that are positively charged and neutrons that have no charge, the center will have a net positive charge. As a result, you expect some of the positively charged alpha particles to deflect at varying angles from the sheet as they pass this positively charged nucleus. You'll also expect most of the alpha particles to go right through the sheet if most of the atom consists of empty space with negatively charged electrons orbiting around the nucleus, as proposed by the third atomic model. If the other two atomic models are correct, you shouldn't be able to detect any deflection, since the positive charge for them is not concentrated at any point. You can also see it this way. Each proton carries a positive charge of plus 1.6 times 10 to the power of minus 19 coulombs. And 13 such protons are tightly packed into the nucleus. This creates a region of strong positive charge around the nucleus that repels and deflects any alpha particles. Similarly, each electron carries a negative charge of minus 1.6 times 10 to the power of minus 19 coulombs, which is spread over a very large area, creating a negligible impact on the alpha's particle's path. Also, since each proton and neutron has a mass of 1.67 times 10 to the power of minus 27 kilograms, that's pretty small. Having 27 of them packed into a nucleus means that the alpha particle isn't going to be able to budge them, because them being heavier than an alpha particle, and be deflected instead. However, each electron only has a mass of 9.11 times 10 to the power of minus 31 kilojoules, about a 2,000th of the mass of a proton, which is really 0.0125% of the mass of an alpha particle, which means that any collision with an electron will also not cause significant deviation in the path. In short, if the third model is correct, the alpha particles will detect at multiple different angles from the sample as well as directly behind it. On the other hand, since the other two models have very dispersed charges or no charges at all, it's unlikely that it will be able to deflect any of the positive charge alpha particles away from the sheet. Your clever ingenuity has paid off. It took a few tries, but you were able to use the experiment to detect alpha particles getting deflected at various angles from the aluminum metal sheet. That showed that the third model was the correct one. What you just performed is called Rutherford's alpha particle scattering experiment, and it helped pave the way for some very interesting insights into the atomic structure. Now, can you solve this next brain teaser? The specific charge of a particle is defined as its charge per unit of mass and is denoted by coulombs per kilogram. In other words, how much charge does a particle have for every unit of mass that it has? Using this, can you calculate the specific charge for a proton and an electron?